So this image here that you're looking at is known as the Hubble Ultra Deep Field Image. And we're by NASA from about September 2003 through to about January 2004. Through a period of about quite a few orbits of the Earth, they pointed the telescope, the Hubble telescope, at a very small patch of seemingly blank, featureless sky. The patch of sky was so small, it was the same as size if you'd held a grain of sand at arm's length. You imagine that, a grain of sand at arm's length, how small area that is. Small patch of featureless sky. And over I think it was about 800 exposures with a total exposure time of 11.3 days, that was the result. Incredible. There is 10,000 points of light on that image, each of which represents an entire galaxy of millions, sometimes billions of stars. And what it does to it reflects the enormity of the universe, whereby if you extrapolate that out with that image, they estimate there could be up to 2 trillion galaxies in the universe. And of course, the next question you're probably going to think to yourself is, where do we fit in on all of that? And that's why tonight's talk is titled, Our Place in the Universe, Where Do We Fit In? Tonight we're going to go on a visual tour or journey through the universe, starting off with our little rocky planet that we're familiar with, Earth. We'll move out through the solar system, the Milky Way galaxy, the local group, and then we're going to move out into the Virgo supercluster, into the wider universe. So let's get underway. So we'll start with our familiar home planet Earth. This image of Earth was taken by the Apollo 17 astronauts in December 1972. And it was someone asked one of the astronauts, went to the moon, and said, what did you learn the most about going to the moon? Yourself or maybe humanity, what did we learn the most about going to the moon? And he replied, it was Earth. We discovered Earth. We discovered how fragile and isolated Earth is. So Earth is a rocky planet. It's relatively small in the big picture of things. Diameter roughly about 13,000 kilometres. 70% of its surface is covered with liquid water, which is essential for carbon-based life, and of course gives it that blue marble appearance. And from radiometric dating of rocks, in particular meteorites, it's estimated that the Earth is about 4.6 billion years old. So that's Earth. As for life, Earth is the only place that we're aware of in the entire universe where there is life of any form whatsoever. Scientists have identified over 2 million different species of life form on Earth, and it's estimated there could be up to 8 million species. That was some we just don't know about. Fossil evidence suggests that life got started early on Earth, very quickly, usually about 4 billion years ago. As soon as the Earth had cooled down to a reasonable amount, those early days, it was just a molten hell of lava and steam. But as soon as there was some liquid water available and it cooled down enough, over say 500 million years, life got started on Earth. But for over 3 billion years of that time, it was all single cellular, simple life, probably in the form of slime, essentially. And it was only as recently as about 650 million years ago, that complex multicellular life actually started happening, and we started getting plants and animals and the like. So the message from that really is that life will get hold pretty smartly if it's given an opportunity, but it's usually single cellular life, and it takes a long time for complex life to get going, which it did on Earth. And of course, with humans, what we're all familiar with, and that's what reason why we're here to talk about us, there are over 8 billion humans on Earth. I think that's quite frightening, really. I remember a few years ago on the news where we'd cracked the 7 billion mark, and all these world leaders with champagne glasses toasting themselves. And I remember to stop and think to myself, is this something we should be celebrating? There's so many of us, but there's 8 billion of us now. So a few little milestones with humanity. It's been about 10,000 years that we've been doing agriculture, learning to grow crops and so on, get more efficient at that. With civilization, about the last 6,000 years, we've learned to organise ourselves in large groups and governance and so on. We've been in an industry, has been sort of an industrial revolution about 200 years ago. And we've been in the space age for about the last 70 years. So you can see how things have been accelerating pretty quickly through there since we've been around. So in terms of our model of the universe, we're going back over 2,000 years ago when the Greeks already knew that the Earth was round at that stage. They'd already worked that out. And in keeping with their religion and with their common sense, the observations they made, they had what they called the geocentric model of the universe, where the Earth was at the centre, the Sun and the planets and all the distant stars were slowly moving around the Earth. And that fitted the bill. It did, however, have a problem. It couldn't explain how some of the planets appear briefly to go backwards in the sky before they go forward again, what they call retrograde motion. So it was Ptolemy, the Greek philosopher, who came up with this complex idea of complex circles within circles to try and explain things. And if you're familiar with Occam's razor, if there's multiple possible reasons for something, it's usually the simplest reason. But despite this complex array of circles within circles, they still stuck with it for about 1,500 years. Because it was in the mid-1500s that a Polish mathematician by the name of Nicholas Copernicus first had the insight to realise, hey, there's a simpler explanation for this. You put the sun in the middle, have the Earth and the planets rotating around slowly, them going around the sun, and the same with the stars, called a heliocentric model of the universe that explains everything. But even then in his day that was considered heresy, and of course he didn't release any of his papers with his ideas until his deathbed. Literally the day he died, he then had the courage to release this information. Yeah. So moving out from there, and you're probably familiar with a lot of this. So we have our model of the sun, the heliocentric model, where you've got the sun in the middle, and there is 8 planets, but up until the invention of the telescope, of course, there was only 6 planets. We could only, with the naked eye, see up to Saturn. So we had Earth, we had Mercury, Venus, Earth, and Mars, the 4 inner rocky planets here, and then we went out to Jupiter and Saturn. And Saturn's orbit from the sun is about 1.5 billion kilometres, giving a total span. So if the sun's here, it's orbiting at about 1.5 billion kilometres, giving the solar system a span of about 3 billion kilometres. Remember these figures, by the way, guys, not literally the figures, but just remember the gist of these figures as we go along. So up till the invention of the telescope, the span of the solar system was about 3 billion kilometres. Then in 1781, William Herschel, a British astronomer by the name of William Herschel, who was into building his own very large, for the time, reflector telescopes. And in 1781, he discovered Uranus. And overnight, the solar system doubled in size. It went from a span of 3 billion kilometres out to a span of 6 billion kilometres. Then in 1846, about that time, some people had noticed that the orbit of Uranus was slightly out of kilter. Something was going on. I'll come through, guys. And they had concluded that somewhere out there must be another large planet that's disturbing the orbit of Uranus. And there was a French mathematician, Leverrier, and an English mathematician, John Adams. They both independently had worked out roughly where that planet should be. And it was a German astronomer from Berlin, Johann Galler, who pointed his telescope in that general region, and not too far away from where they predicted it, there was Venus. And once again, Neptune, pardon me, a bit distracted. So there was Neptune, which was you're going out to 9 billion. So suddenly it took another 3 billion kilometre increase in span. The solar system took another big jump way out to a span now of 9 billion kilometres. So that's the span of the planetary orbits of the solar system. And then it came in the 1990s, whereby a whole new generation of telescopes came into commission, the 8-metre to 10-metre telescope, diameter telescopes, and suddenly they could start seeing further out into the solar system. And they realised there were literally millions of small little rocky icy objects all sitting out in the outer reaches of the solar system, that in a sort of a donut shape or a torus shape, if you will, that goes out here, that goes out from between the orbit of Neptune at 9 billion kilometres out to about 15 billion kilometres outward. So suddenly the solar system, just in a few years' time, had just grown again, huge amounts. And they concluded that most likely this Kuiper belt, it was known as, after a famous astronomer, Gerald Kuiper, that this was probably the source of where a lot of comets came from. Remember, comets are these small rocky ice objects that come from the outer solar system, go in through the inner solar system, around Earth and head back out again. And they're split into two groups: short period comets, those that their total orbital period is less than 200 years, and long period comets greater than 200 years. So they concluded most likely these short period comets are coming from this Kuiper belt. So how about the long period comets? Where are they coming from? So there's a hypothesized area of rocky ice objects known as the Oort cloud, a big sort of complex, a spherical complex around the solar system here that millions and millions of these icy objects are, and this is most likely the cause of these long period comets, where they're coming from. You can see here, here's your Kuiper belt. I'm going to put it in here. This time you're going out to a light year in radius. In other words, the whole span 2 light years. A light year being the distance that light travels in a year, which is 10 million kilometres. You suddenly look at the solar system has just expanded hugely out. So there's a lot of evidence that's out here. So that's heading out into the outer parts of the solar system. Just putting, because the sun is so important, into the centre of the solar system, putting it into perspective. And here's a to scale diagram, a size scale diagram of the sun next to the planets Jupiter, Saturn, Uranus, Neptune. There's little Earth there. God, someone's put Pluto in there, bless them. We won't go there, but look at the size of it. Whereby I usually have a little, often I've done it before, as for a little model, I have a little frozen pea as the Earth. And I ate it one day accidentally. I ate the Earth, so I couldn't bring it along. So, but yay big. And to that scale, the sun is the size of a Swiss ball. I used to have a Swiss ball with me, about that big, to tell how to scale. The Earth will fit into the sun volume-wise 1.3 million times. So the solar system, despite all this talk about planets and so on, it's all about the sun. A little bit about the sun. This is a real image of the sun in some detail. It's taken by NASA's Solar Dynamics Observatory. So astronomically, the sun is considered a G25 star. The G2 bit refers that it's got a surface temperature of 5,800 degrees. And the V part, for Roman numeral for 5, automatically means it's on what we call the main sequence. The main sequence is a relatively stable stage in a star, where all stars spend the first 90% of their life. And by definition, their cores are fusing hydrogen into helium. Hydrogen being the most lightest element in the universe, and it's fusing that together to create the next lightest or smallest atom, the helium nucleus. And in the process, bits of mass gets lost, and that mass gets converted into energy to create the heat and light that we experience. So out of that hydrogen fusion, 600 million tonnes of hydrogen gets fused and burnt up per second in the sun. 600 million tonnes. Every time you blink your eyelid, 600 million tonnes more of hydrogen is being burnt up. And that gets converted into 596 tonnes of helium, which means that 4 tonnes of energy per every second is being lost. And that 4 million tonnes of lost mass per second is more than 1 million times humanity's annual energy consumption. So all the energy that all of humanity uses up in a year, the sun produces over 1 million times that every second, just by 4 million tons of mass being lost. So it just puts everything in perspective and puts planet Earth in perspective too, of us just in the solar system. So let's move out from the solar system. So our star system is only one star out of about 400 billion stars that go to make up our Milky Way galaxy. So a galaxy refers to a collection of stars and gas and dust and other astronomical objects that are all gravitationally bound, held by gravity into a certain structure. And the Milky Way galaxy is what we call a spiral galaxy. It's a disc shape or a plate shaped, if you will. And this is a photographic view here of us looking back towards the centre of the Milky Way. There's some dust lanes through here. You can see the big, dense, bright, glowing central bulge of the Milky Way. And it was Galileo who, in the 1600s, when the telescope was first invented, he was the first person to point it up at the sky. And it had just been called the Milky Way because it looked like a big blur of spilt milk. But he was the first person who put the telescope up there and had the insight to realise that what the Milky Way was just millions and millions, countless numbers of stars that are just so distant that we couldn't resolve them with our eyes. So he was the first person to have that insight. And of course, he got done for heresy too, didn't he? Because it didn't apply to everything. So that's our Milky Way galaxy. Now, we sit about halfway out. This is a photograph image of the Andromeda galaxy. That's our nearest large spiral galaxy. Of course, you can't take a picture of the Milky Way because we're in the middle of it all. So this is a nice standard. The Andromeda galaxy is about 40% larger than the Milky Way, but very similar otherwise in structure. So I've used this image here as an analogy for the Milky Way. So the Milky Way in size, here's your nice big sort of disc-shaped galaxy. From here to here, you're talking about 100,000 light years. And here we were thinking, wow, the solar system has just moved out to a span of 2 light years. The Milky Way galaxy spans 100,000 light years. Remember, one light year is 10 million kilometres, and this is 100,000 across. From the centre, we're about 26,000 light years out from the centre. So in other words, very roughly about halfway out. So that's us in the Milky Way galaxy. So up until 1924, it was just generally considered that all the stars, all the objects that we could see in the sky were all within the Milky Way, and the Milky Way was the universe. That was it. There were a few patches, fuzzy little patches, however, they called them nebula. The word nebula in Latin means mist. So they looked very misty little patches called nebula. And they had names to them depending what constellation they were in. And they weren't really, the telescopes at the time hadn't been powerful enough to really resolve much more about these little nebula. And it was Edwin Hubble, yes, as of Hubble Space Telescope fame. It's been named after him. In 1924, he used the Mount Wilson in California, the 100-inch telescope, which was by far the largest telescope in its time. So 100 inches, that's about 2.5 metres. So, that's sort of a reasonable, sort of that corner through. That's a large size mirror to be looking through, particularly for its time. And he was looking at a patch of the sky called the Andromeda Nebula. It was an Andromeda constellation, and it was one of these misty-looking nebulas, sort of objects that they didn't really know much about it. And he was able to resolve some of the stars. And this is from his original plate and his original notes he made to himself. And he noticed some 3 spots of light, one here, and one in here. And he noticed that they appeared to be new spots of light. So he labelled them on the plate N for nova. Nova refers to new light. It's usually explosion on the surface of a star. So he recognised that no one's really made note of these on previous plates. These must be new. So he labelled them N. And then as he went through some of these older plates that he'd done in the library, he noticed that this star here actually was on previous plates, but it was a lot dimmer. In other words, there was a normal star there. It wasn't a nova. It was fluctuating in its brightness. And he recognized that, hey, this is a variable star. And you can see where he's crossed the N out and put VAR, exclamation mark, for variable. So what got him excited? What got him excited? He recognized this variable star as what they call a Cepheid variable star. And it's a type of star that an American astronomer lady by the name of Henrietta Leavitt, who a few years prior had shown, which is now called Leavitt's law, that these particular group of variable stars called Cepheid variables, the rate at which they get brighter and dimmer and brighter and dimmer, their period or rate, if you will, is directly related to how bright they are, how intrinsically bright they are. They're what they call your absolute magnitude. Not how bright they appear from us, but actually how physically bright they are. The longer the period, in other words, the longer they take to get brighter and dimmer and brighter and dimmer, the more brighter their intrinsic brightness is. So, of course, he now knew that. So he then recorded the brightness, what he called the apparent brightness, how it looks through your own telescope from Earth. And there's a very simple formula. Once you know how bright something really is and how bright it looks from us through your telescope, there's a very simple formula. You just work out the distance. So he worked out the distance to the Cepheid variable. He got at the time 800,000 light years. It's a little bit shy of the mark. There's a long story behind that. There's different types of Cepheids he didn't know about at the time. But we now know it's about 2.5 million light years away. But needless to say, his calculations said it's 800,000 light years away, which was still, the point being, it was a no-brainer. That was not in the Milky Way galaxy. That was a far, far away object. And for it to be a reasonable size in the sky, that was a massive object. It was so massive, far away. Clearly, that was another galaxy. And it was that moment we realized that the Milky Way is not the universe. It's just one of many galaxies. They call them island universes scattered throughout the galaxy, throughout the universe rather. And it was just with more observations, with further telescopes as time went on, they looked more at these little fuzzy little nebula and they realized there's loads and loads of galaxies out there. So it was at Hubble in 1924 who first did that discovery. So suddenly the universe had grown hugely amount in size. Now, the Milky Way, then they realised there's roughly about 80 galaxies that are all sort of gravitationally bound together in a group. It's called the local group. You probably heard of the word galaxy clusters as well. Not to be confused, you hear galaxy groups and galaxy clusters. One and the same. The word group is just used to apply to a smaller group, less than about 100. Less than 100 galaxies all sort of together, gravitationally bound together, you call them groups. Greater than about 100 or so, you call it a galaxy cluster, just to get that term sorted out. So they have slowly identified, this is sort of like a 3D type map, they put the Milky Way in the middle here, and it's called the local group. It's about a collection of about 80 galaxies that are all gravitationally collected. There's 3 decent-sized spiral galaxies. There's the Milky Way, there's the Andromeda, known as M31, that's about 2.5 million light years away, and then there's the triangulum galaxy M33, which is about 2.7 million light years away. That was the M stands for Messier. Charles Messier was an astronomer who started cataloguing all these fuzzy objects. He was a comet hunter, so he wanted to catalogue all these funny objects in the sky so they wouldn't get confused with comets. So he there was over 100 of them that he catalogued. So he obviously saw these. He labelled that one M31, M33 and stuff. Little did he know he was cataloguing entire galaxies. So the local group is 10 million light years across. So remember the solar system, we started talking in billions of kilometres, and then we went out to 2 light years, and then we went out further again to the Milky Way galaxy at 100,000 light years. You're now into 10 million light years across, and that's called the local group of galaxies.
Those the circles there, were they in 2 million light year?
Let's just go back there a minute.
I just couldn't quite read the...
Oh, okay. Oh, these circles here, I think they are... Yeah. Yes, it's in light years, yeah. It's 10 right across, so it's 5 from here each way, so they are in light years. So it's going 5 that way and 5 that way, because it's 10 right across. It should be. Okay, so now the local group, you think that's big, 10 million light years. We are then, that whole local group is just one of 100 groups, or clusters if you will, forming the Virgo supercluster, which is, never mind 10 million light years, this is 110 light years across. So suddenly we're just paling into insignificance pretty quickly. An interesting little feature about superclusters, they are not bound by gravity. They're bound to what we call the Hubble flow, which is just the natural flow of the motion of galaxies through the universe due to the expansion. The universe is just expanding, not to be confused with the expansion of dark energy. This is just the coasting outwards from the original period, what we call inflation, when the universe went through an initial period of rapid growth, and there's just a coasting effect. So that's what they call the Hubble effect, and it's that effect that keeps superclusters together. And there's some evidence to suggest the Virgo supercluster is then part of the Laniakea supercluster, which has a diameter of about 520 million light years. So we're just leaving all these other figures, we're just leaving behind in the dust. They're on very, very large scales, as in actually that meant to be millions, thousands of millions of light years going right across. You get this large web-like appearance, and here is right in the middle, here's the Virgo supercluster here. But look at all these superclusters, big clumps of them here, lined in these walls, sheets and filaments, they call those, with little nodules as well, but sheets and filaments with these big, relatively open spaces between, known as voids. And they call it the cosmic web, because it looks like a web, or a soap suds, if you will, or a sponge, or something like that. But you get these big voids, and you get these sheets and filaments of these large superclusters forming. So that's on a much, much large scale. You're talking here thousands of millions of light years across. You might think, wow, so this is a diagram of it. How certain are they of this? Well, there's a telescope in New Mexico known as the Sloan Digital Sky Survey at Apache Point. It's this telescope here. It's a 2.6 meter telescope, and it's wide-angled, and it's dedicated just to constantly scan the sky. And for every galaxy it sees, it maps the position and the distance to every galaxy, such that it can forming a 3D map of all the galaxies and the galaxy clusters and the superclusters in the universe to create 3D models. And this is some real data. That is the arrangement of superclusters. That is real data from the Sloan Digital Sky Survey. So you can see there, look, all these sheets and filaments of clusters and superclusters with these sort of voids in between hand. So that's actually the arrangement of the universe as they see it on extremely large scales. And I've got here a nice little movie clip how they've put it together. This is only for about half a minute or so. And you'll be travelling through, it's like a virtual tour. So this is using real data that they've put here into a small short movie. You can see there's all your voids here. Like here's a nice sheet filament of galaxy clusters. So that's real data. You can sort of make it out there, doesn't it? It looks like a web. I can sit and watch that all night. It's pretty cool. So just think back when you're looking at that. Go backwards to the Laniakea supercluster, Virgo supercluster, local group, Milky Way galaxy, our solar system. You go back through there, and we're just a nothing. So the next question you might say, well, okay, let's look at the whole universe. How big is the observable, or the whole universe? How big is it? And the answer to that is easy. It's the distance light has travelled since the beginning of the universe. Easy. But to answer that question, to provide that answer, you need to have another question. You've got to know the age of the universe, or a little bit about the universe. Does it go on forever, or did the universe have a beginning? And it was our friend again, Edward Hubble from the Hubble Space Telescope fame, that he was able to determine that the universe was expanding and the age of the universe. So it was 1929 that he discovered that distant galaxies, way in the distance, are all receding away from us. And the more distant galaxies were receding faster away than the more closer galaxies. And the conclusion is, there's only one conclusion to make from there. The universe is expanding. And he was able from there to measure the rate of the expansion. That's what he did there, was able to plot. So he got numerous galaxies, and he plotted the velocity on the y-axis as a function of the distance to the galaxies on the x-axis. And it formed a nice straight line there. So here it is here, the galaxies further away from us. The velocity at which they're receding is much, much higher than galaxies at a short distance to us are travelling away a lot slower. So that was pretty much indicating that the universe, the only explanation for that is the universe is expanding. And the slope of that line is the rate of expansion, known as the Hubble constant. So once again, his calculations weren't quite, because the instruments weren't quite refined. It didn't come to today's standards, but he was able to get a reasonable idea of the age of the universe, which we now, the modern estimate's about 13.8 billion years old, very, very roughly. And this here is a diagram, an artist's impression of the history of the expanding universe, which is worth talking about, known as the Big Bang. And the Big Bang, a lot of people get this confused. They think the Big Bang dictates the whole beginning of the universe. The Big Bang theory, all it says is that the universe was much smaller and hotter than it is today, and it's been expanding. It says nothing about how the universe came about to being. We're into quantum fluctuations and quantum bubbles and all sorts of things. That says nothing about that. It just says the universe was once very small, is now expanding. So it went through this phase of very rapid growth in this first split of a second called inflation, expanded rapidly, and then it's just been expanding slowly since then. There are what they call the four pillars of evidence for the Big Bang, that the universe is expanding. One is that Hubble discovered all the distant galaxies are all travelling away from us, and the further they are, the faster they are. That's point number one. Two is the universal abundance of elements. They were able to, with the laws of physics, work out the conditions in the first few minutes of the universe's being, how hot it would have been, how the collisions that would have been occurring, the particles that would have been there, and they had an idea, and they could work out how much hydrogen would have fused under those conditions into helium. So the abundance of hydrogen, helium, and the relative isotopes in there. And they match perfectly with what we see in the universe today. Just matches perfectly with what they estimate would have happened in those early conditions. So the universal abundance of elements. The third one is quasars. Quasars, you've probably heard of supermassive black holes, big, massive, millions of solar masses, sometimes billions of solar masses at the centre of most decent-sized galaxies, and they can become active and become sort of active galactic nuclei. Quasars are similar in principle, but totally different beasts. They're like super active, supermassive black holes on steroids. They are massive, 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 and they are powerful, powerful, powerful. And you look back into the early universe, when the universe was just a few billion years old, and you see many of these massive quasars just blazing away. And as you come back to the more recent universe, you see fewer and fewer and fewer of them. So that automatically tells you that the universe has been changing, it's been evolving. It tells you that. Loads and loads of quasars once, now no visible quasars in the local universe, less and less. The universe has changed, it is evolving as we talk. And the fourth very powerful bit of evidence was what we call the cosmic microwave background, which we'll talk a little bit about now. It's a very powerful thing in science. If you come up with an idea and a theory how something might have been, and you're able to make a prediction, if that is so, we should be able to observe this over here. And if you do end up observing that over here, that's a very, very powerful indicator, bit of evidence that you're on the right track. So with the Big Bang, when the universe was very hot, the best way of doing this is me just taking a step back and explaining. In the first 380,000 years or so, with the laws of physics says it was just the universe was just a hot sea or soup of charged particles, electrons and protons, just all smashing into one another. The temperature was too hot whereby they couldn't combine together. So they're just bouncing off one another. Light was in there too, light particles bouncing in around there. So the universe was opaque. It was visually opaque, a dense, opaque soup of charged particles. And as the universe was expanding and cooling down, it got to roughly about 380,000 years old. It cooled down sufficiently for the protons and electrons to start being able to join up again. So you had, well, I use the word again, they use that term recombination, but it's only happened for the first time. So the protons and electrons can join up and suddenly you've got neutral particles. Suddenly the light particles were free to travel across the universe. This was the very, very first light of the universe when it first became transparent. And they worked out from there the temperature would have been roughly about 3,000 degrees, the universe would have at that time, which means the light would have been in the sort of red part of the spectrum, peaking in the mid, so rather peaking in the near infrared and then spreading out from there. So that's what the wavelength of light would be. Light is made up of waves of electrical and magnetic energy. And it's what we see about in the middle, somewhere visual light, and as you get shorter and shorter wavelengths of higher and higher energy, like your ultraviolet, your X-ray, at the other end, you get longer and longer wavelengths of less energetic, infrared, microwave, and radio wavelengths. Hence, you know, they don't hurt you. You're remote control. It's not going to do my my hand any harm. It's just long wavelength light, low energy. So they then predicted this very first light that was released. The universe has expanded about 1,100 times over since then. So the wavelength of light, as it's travelling, as the universe is expanding, that wavelength is travelling through the universe, and that wavelength is getting stretched out at the same time as part of the universe expanding. The wavelength now should be in the microwave part of the light spectrum to reflect a temperature of about 2.7 degrees Kelvin. So that was in theory. So the race was on to try and find this, because this is a crucial bit of evidence. And it was just by chance, these two here, Arno Penzias and Robert Wilson, in 1964, they were working for Bell Laboratories, communications, and they were experimenting with the microwave part of light to see if they could communicate. And they had this huge, big horn-shaped sort of antennae dish that you can see behind them there. And they started getting all this crackling noise. They just couldn't get rid of it. They thought there might have been pigeons nesting perhaps up there or soiling it. So they cleaned it out, shooed the pigeons away, cleaned it out, and still there's this background noise going on in microwave wavelengths. They were wondering what was going on. And it was an astronomer just down the road in Princeton, Robert Dickey, who was one of the theorists, who heard about it. He says, "Oh my God, we've been beaten." They raced down there, and sure enough, these guys had discovered the cosmic microwave background. Remember your old analog TVs in the 1960s and stuff? Between channels, it was all fuzzy and stuff. A lot of that was the cosmic microwave background that you're picking up on your aerials. So they did discover it. So that was a powerful tool that sort of backed up our age of the whole universe, how old the universe is, how big it is, and so on. That was a huge step forward. So since then, they've sent out some satellites above the Earth's atmosphere to get a much more accurate view and to analyse this cosmic microwave background. From here, you just look like there's a series of speckles in there. But each of those little speckles represents fine, tiny, tiny little variations in the temperature or the wavelength of that microwave wavelength, up to 1 in 10,000 of a difference, all those little speckles. And if you analyse them, they put them into histograms, it's subject of a whole different talk. Needless to say, there is a lot of information in this very first light. They call it the permanent imprint of the early universe when it was 380,000 years old. This is the very first light that you can still see now. And it gives a lot of information you can analyse from all that into the amount and the distribution of matter and energy that was in the universe at the time, and also the geometry of the universe, and that's important. It's a whole different story. You can tell how much dark matter was in the universe, how much dark energy, its geometry and so on, from analysing all those speckles. So it's a huge step forward with science. So let's get back to our question, how big is the universe? And you've got to consider the observable universe and the entire universe. And the observable universe refers to the distance that light has travelled since the universe began, 13.8 billion years. So first of all, we had to ask that question. Is the universe expanding? We know that now. How old is the universe? You just calculate backwards, by the way, and it comes to about 13.8 billion years. So you'd immediately think, well, it's 13.8 billion light years, isn't it, across? But don't forget the universe has been expanding over that 13.8 billion years. So with a whole stack of complex calculations and stuff, it actually the answer is that since the universe is expanding, we're observing objects about 46.5 billion light years in each direction. So we put the Earth in the middle, and we're seeing objects that are about 46.5 billion light years that way, and that way in all directions. So in other words, the observable universe, in other words, the area of the universe that we can see since the universe began is 93 billion light years across. Once again, run that back through your mind into superclusters and galaxies and stuff. So that's the observable universe. So how about the entire universe? So if the observable universe is only the objects that we can see, that light has travelled to us from the last 13.8 billion years. What's beyond that? It's the entire universe. So the observable universe and what lies beyond it is the entire universe. And it's the cosmic microwave background that we looked at all those speckles, and I mentioned there that they can get an idea of the geometry of the observable universe. And that data suggests that the observable universe appears to be flat. We can't see any curvature in it. Curvature going either way. We can't see any curvature. It appears to be flat. So which leaves the entire universe as one of three geometries. It's either completely flat, going on indefinitely in all directions. And these are two-dimensional, of course, but you've got to think in 3 and 4 dimensions, which is hard to get your head around. So we've made it nice and simple here with these two-dimensional. But it's just flat in all directions, goes infinite. Or it's curved open and infinite. This is like a horse saddle where it is curved, but it goes out like that, and it is infinite, just goes on forever. Or it's got a closed curvature, like a sphere, and it is finite. Now, the laws of geometry says, we all know that if you get something around, the Earth's a classic example, we know the Earth's round, but you get a small enough region. If you're small enough, like we are on the surface, looking at a certain distance, it appears to be flat. And like if you get a beetle on a basketball or something, the beetle would tell you that ball is flat, but we stand back, it's not. So the laws of geometry says that if you've got a spherical sort of object, a closed spherical object, and you've got a region that appears to be flat from the surface, the closed curve must be at least 250 times the size of that observable aperture. It may well be more, but it has to be a minimum of 250 times that. So, which means the entire universe, even if it's closed and finite, still has to be at least 23,250 billion light years across. That's the bare minimum it has to be, if it's not infinite. So, the conclusion is the entire universe is extremely large. So let's just go home and wrap up with our Earth. So if you think you're special, you're 1 in 8 billion human beings. And us humans are one of 2 million known species. Planet Earth is one of 8 planets, about 13,000 kilometres across, which is part of the solar system, which is about 2 light years across. And our sun is 1 in 400 billion stars that go to make up the Milky Way galaxy, which is 100,000 light years across, and is 1 in 2 trillion galaxies in the universe. The observable universe, we know, is 93 billion light years across, and the entire universe is at least 250 times the observable universe. And that's our place in the universe. Thank you. Are there any questions around that? I've got some handouts, by the way, if you want to pop in that, you're welcome to some handouts. Any questions around any of that?
Your piece on the I can have a couple of questions, I guess. The first one is, if you go to the edge of the observable universe, which is from our perspective,
yes,
as we see it, right? If you're on the edge of the observable universe, from what we know, that point would also have a 48 million light year radius as well.
Yes, correct, yeah.